We know that matter is made of particles, and incredible machines such as the atomic force microscope allow us to visualize individual atoms, and electron microscopes let us infer even greater detail. But looking inside the atoms themselves is an entirely different matter. The alpha particle scattering experiment was astounding, as it showed us that atoms, the building blocks of matter, actually contained much smaller particles, nuclei. We then found that the nucleus was made of neutrons and protons, by firing even higher energy particles in and breaking them up. These were looking like fundamental particles, but then what about beta radiation? A neutron changes into a proton. How is that even possible? Once we could make even bigger, more powerful particle accelerators, we're able to smash our way inside the protons and neutrons, and we found that they were made up of fundamental particles, quarks. At the moment, we don't have a tool powerful enough to look inside the quarks, so we are going to consider them as fundamental particles. We're still going to look into beta radiation in more detail, but we need to look at these nucleons first. First up then, the neutron and the proton. Relative mass of 1, and the proton has +1 relative charge. The neutron is neutral, no charge. There are a few properties we need to understand if we're going to look at other more exotic particles, so let's look at these familiar ones first. So, the mass, which we normally are going to measure in kilogram, but the proton is 1.673 times 10 to the minus 27 kilograms. And the neutron is 1.675 times 10 to the minus 27 kilograms. So these are very low masses, and particle physicists don't really want to have to write 10 to the power of minus 27 100 times on every single page. So there is the unified atomic mass unit, U. 1 U is 1.661 times 10 to the minus 27 kilograms, meaning that the proton is 1.007 U and the neutron is 1.009 U. Now, you might be wondering why neither of them are exactly 1 U. That would seem pretty sensible. Or instead, why is 1 U not the average of the proton and the neutron? The short answer is that 1 U is defined as being 1/12 of the mass of a carbon-12 nucleus. So, that's a nucleus, meaning there are no electrons. It's a nucleus with 6 protons and 6 neutrons. It has 12 nucleons, and we define one unified atomic mass unit as being 1/12 of the mass of this carbon-12 nucleus. Now that still doesn't explain why 1 U is smaller than either a neutron or a proton, and for that we need to go to A2 physics and Einstein's work. So you don't need to know this now, but basically, if you take a carbon-12 nucleus and you separate all the neutrons and protons, it requires energy. Okay, you're breaking up that nucleus, so you're going to need to put some energy in. That energy has to go somewhere, it's going to be stored somewhere, and it actually gets converted into mass, following E equals mc squared. So all the protons and all the neutrons get that little bit heavier. And that also means our values of mass for the nucleons should really be defined as the rest mass of an isolated proton and the rest mass of an isolated neutron. Don't worry about the explanation, you just need the definitions. That equation, E equals mc squared, also means we have another unit for mass. Now it's a long explanation, so I'll put it in another lesson video. But the result is that 1 mega electron volt over c squared is equal to 1.8 times 10 to the minus 30 kilograms. So far we have managed to get 2 new units for mass, along with the kilogram. We have 1 U, which equals 1.661 times 10 to the minus 27 kilograms, and 1 mega electron volt over c squared, which equals 1.8 times 10 to the minus 30 kilograms. The other properties that we need to be worried about are charge, which is written in terms of the elementary charge of 1.6 times 10 to the minus 19 coulombs, or E. The baryon and lepton numbers, which I'll get onto next. And strangeness, which I'll cover after that. Neutrons have no charge. They are baryons. They are not leptons. And they are not strange. Protons have charge plus 1e. They are baryons, not leptons, and are not strange either. Simple. This means we can now at least talk about these particles properly and clearly, because if we don't have the right terminology, we're going to find it very difficult to describe what is going on. Next up, we're going to have a lesson video where we're going to look in more detail at those mass units and the energy units, and then after that we're going to continue applying what we've learned so far to understand the world of quarks.